Perfect.
Okay. Oh, and if it starts making a funny sound, could you let me know?
So welcome to the afternoon session. And our first speaker this afternoon is Pevtsova, who will give her second lecture on support theories for the stable modular category of a finite group scheme.
Thank you. And thank you again for the invitation. Okay. So I'll try to be a little bit more systematic today. Start with the first part of lecture 2. And this will be an informal formulation of the problem I want to solve. And then we'll get to the formal one. So, as usual, G is going to be a finite group scheme, and my field will always have characteristic T. We're going to assume it's also very closed. Then, as I'm sure is widely known, the representation category of G is usually wild. Except for a few nice cases, such as the cyclic group, or this first Frobenius kernel of GA. So very small ones we understand. So these guys have finite representation type. But if you go just a little bit further, something like Z mod 3 covers Z mod 3, has a wild representation type. So usually representation type is wild. Also, the second Frobenius kernel, also wild. So, we have no hope, basically, to classify indecomposable modules or to classify modules up to direct sums. Okay. But maybe the question is sort of too fine. Let's see. Cannot classify up to direct sums. So how about instead of trying to classify up to direct sums, we take our inspiration from topology and try to classify modules up to homological operations. We will allow taking extensions, taking syzygies, taking direct sums, or just direct sums, depending on whether we are in a big category, in small category. And again, taking the terminology from topology, you can ask this in the following way. Let's say we have two representations of G, then when can we build M out of M using this homological operation? So you start with M, you can take extensions, you can take direct summands, you can take syzygies. When can you get to M? So instead of just taking direct sum, we allow ourselves way more operations. Now it turns out that this question is still too hard, at least for an arbitrary finite group scheme. So we add one more operation. We throw in tensor product. So we also allow tensoring with a simple module, And I should probably mention that for finite group schemes, you only have finitely many simple objects. You always have finitely many simple objects. Okay. So we allow these things, and we ask when we can build M out of N. And this question does have an answer, and basically, proving the answer is going to be the goal of the next 2 lectures. And the answer is very simple. We can build M out of N if and only if we have that support of M is inside the support of M. Now there's probably at least one problem with this answer. I haven't yet said a word about what support is. But it is a geometric invariant of representation, and what I'm going to do today is describe this invariant. Today, we'll define what support is and describe its properties. And
the mic is out.
mic is out. Thank you. What now? No. Any chance it just needs
Yeah, I think it can go back. Who happens to have a couple of vague patterns?
Okay, good. Thank you. Is it still okay? I guess? Yes? And the last lecture will be about the proof of this. Okay, now this is sort of informal. I'm going to reformulate the problem in the formal language. And Rio basically set up everything I need for this yesterday. So I'll just quickly probably do it again. So the formulation problem. The formal formulation. And let's say of the building problem. So we're going to work in the stable module category for G. Let's recall that this is a category where the objects are representations of G or KG modules. And for the morphisms, we take morphisms in the category of G modules, and we factor out the ones which factor through projective module. So these are those which factor through a projective. Now, we are more algebraically oriented. Oh, right. This is the big stable module category. I'm going to use the same convention. When I have capital letters, this means all modules are included. There is also this small stable module category. So these are only finite dimensional modules, but the same definition. And these are precisely the compact objects in the big stable module category. And now, if you're more algebraically minded, can give you a different definition. Small stable module category. It is a category of singularities of representations of G. So if you take the bounded direct category of G modules, representations of G, have a localization sequence where this one goes the singularity category of G. And here we have the perfect complexes. Representations of G. And the fact that the singularity category is the same stable module category as is attributed to Rickard. You're talking to representation theorists and Buchwald. You're talking to community algebras. Okay, so that's the category we want to work with. This category is tensor triangulated. And Leo gave us a definition of what it means. I'm going to use this notation for tensor triangulated. So it has the triangulate structure and the tensor structure, and they're compatible. Tensor structure is the same as for representations. You have two representations, you tensor them over K. It descends to here. Just one thing I want to mention is what is the shift in this category? Omega minus 1, and it's just a scissor shift. So if you have representation of G, you embed it into its injective hole, and you take the co-kernel, and you get the first scissor G, or minus first scissor G of M. It's also called the Heller's operator, and that's the shift operator. The triangles come from exact sequences. The tensor product is a tensor product of G modules. Now, since it's a tensor triangulate category, we have the standard notions which were all defined. So I put them on the board there just to remind you. Here. So in this category, we can have fixed subcategories. This is a full triangulated subcategory. In the small stable module category, we look at fixed subcategories which have full triangulated subcategories closed under direct sums. In the big stable module category, we look at localizing subcategories, which are again full triangulated closed under direct sums. And then the subcategory is a tensor ideal if we take anything from the subcategory and anything else from tensor, you land in this subcategory again. Another problem that I'm interested in problem of building one module out of another is stated as the following. When we classify thick tensor ideals in a small stable module category, so to classify thick tensor ideals, you think through the definition would mean exactly the same thing as to say when we can build one module out of another. Because what goes into the definition here are precisely my allowable cosmological operations that I mentioned in the informal section. And also, for the big one, we want to classify localizing tensor ideals. One thing I want to point out is that even though the first problem is strictly about finite dimensional modules, the only method we have at our disposal uses in an essential way infinite dimensional modules. So that's the reason that once I get to support theories, I actually need to construct them for both finite and infinite dimensional modules, even to solve this problem. And they come up in a natural way, which I'll explain. Any questions? I'm going to say a few more words that you heard in Rio's talk already, namely, mention some of the history of this problem. So it goes back to the stable homotopy theory. And the work of Devenaz, Hopkins, and Smith. Classified big subcategories in a category of finite spectra. And this sort of started a lot of it, and some of the methods go back to this work. Then, let's see. A is a commutative ring. Then Hopkins observed that the method actually worked for classifying thick subcategories in here, bounded derived category of A modules. And then, well, many of you probably know the story. Newman corrected what Hopkins did, and then he also extended it to the infinite category, unbounded derived category.
You should reverse EBA with KB project. You should reverse EBA by KB project. Hopkins and Newman
Oh, you want to?
classifies big categories of KB project, not DB.
Okay. Thank you. So this is commutative algebra. Then Thomason sort of extended Hopkins' result to the geometric context. We look at the category of perfect complexes of coherent sheaves on the scheme X. Let's say in a theorem scheme, put some conditions on X. So here, Thomason really classified tensor ideals. Here, everything we look at is automatically tensor ideals, so one doesn't have to worry about that. And then the representation theory. For a finite group G, Carlson, Benson, Carlson, and Rickard classified tensor ideal subcategories here. I'm not putting years, so this is 97. And all this was before. And then for the big stable module category, I think it's in the paper appeared in 2010, Benson, Iyengar, Krause, I'm going to abbreviate as AK, classified localizing tensor ideals in there. Now, the proof here was very nice and very algebraic. Hopefully we'll have time to give a new proof of this classification, which will be completely different, and we'll use ideas coming from topology. So one thing about this proof was that couldn't find any way to generalize it. To finite group schemes. Okay. Oh, and I should say that I know there are many, many more classification results in the literature right now, and there are people in this room who did classify thick tensor ideal subcategories, localizing subcategories, thick subcategories in various contexts who I don't mention. I apologize. I think I am going to write a survey article for this workshop, and I'm happy to mention there any work I'm not aware of or I'm aware of. So please let me know if I should have mentioned it. Okay. Now we also learned from Rio's talk about the Balmer spectrum, of the axiomatic theory of support. That Paul Balmer constructed, where you start with a tensor triangulated category, and without using anything, just the categorical structure, you construct the support theory, and you say that this data classifies thick tensor ideals. So your category has to be essentially small. For an arbitrary category, it doesn't give you sort of a palpable answer. You need a model for your support theory to know what the answer is. But it certainly tells you that to classify thick tensor ideals, you need to have a good support theory. So if you get a good enough support theory to identify it with the universal one that Balmer constructs, then you're in good shape. Then you have the answer to the classification problem. And so this is what I'm going to do. I'm going to construct a good support theory. In fact, it turns out that to have a good enough support theory, I need two. And these support theories need to work for infinite dimensional modules once again. Which makes the task somewhat more difficult. So my two support theories are going to be the BAK support, local cohomology support, and this comes from the classical cohomological support. Support varieties, which are defined. And the other theory is what we call phi support, which comes from Carlson's rank varieties for elementary binomials. Now, when I say that I need a good enough support theory, there's actually something very precise one has in mind. There is a list of properties that the support theory must satisfy, which would make it Balmer's universal support theory. And the properties. I want to construct supports of modules which satisfy this list. So I don't know, should I go over it? So there are first four properties, which are pretty standard and usually are pretty straightforward. We are in a triangulated category, so if we have a triangle then the support should behave well with respect to the triangle. The support of any modular triangle should be in the union of the supports of the other two. Should behave well with respect to direct sums. It should be invariant under shifts. It should detect when module vanishes. If your module vanishes, support should be trivial and the other way around. So it should be good enough invariant, faithful invariant. We need tensor product property. So the support of the tensor product should be the intersection, sometimes also called the intersection property. And finally, we need the realization property. So for any, okay, let me see. I probably should the context. Right, I have my tensor triangular category T, the big stable module category, and the little stable module category is a compact object. Now X is going to be the spectrum of category. So I need some topological space in which the support is going to live. Now, for a finite group scheme, I should know what this topological space is going to be. And it will be the proj of the cohomology ring. So the ambient space here in which the support theories will be constructed, X is the proj of the cohomology ring. So any closed subset must be realized as a support of some finite dimensional module. So once again, I need enough modules for my support theory. And basically, if you have these properties, then in a relatively formal way, using BAK theory, you can get to the classification, which I'll actually show tomorrow, I think. But the first task is to construct support theories. And let's start with the classical one. Okay. Okay. I didn't mean this when I said classical, although I think the word classical has various definitions. I was once told that you can only say classical when you refer to work by someone who's not alive anymore. But that is definitely not a very good definition. Another suggestion I heard was that you have to wait for at least 20 years. So the work has been around for 20 years and it can be classified as classical. So here the classical support variety, which I'll refer to as cohomological, is the following invariant. Then we start with representation of G. This is going to be finite dimensional representation. Then the homology algebra acts on the X group M. We take the annihilator of this action. So this is by another product. We talked about that. We take the annihilator. So homogeneous ideal. And we say that homological support of M is simply the set of zeros of this ideal inside the proj of the homology ring. So I'm only looking at homogeneous prime ideals here, excluding the irrelevant ideal. We can also alternatively describe the annihilator as simply taking the kernel of the canonical map from the cohomology ring, which is the X from K to K, to the X group, where the map is independent. So I think this goes back to Alfred and Evans, the 80s, so can be classified as classical. Also, John Carlson, and this was done shortly after Quillen's work. So when we realized that they can explore his geometric methods further to benefit representation theory. But this is a nice geometric invariant. By definition, it does sit in the product cohomology, which is my space X here. Unfortunately, it has two problems. The first problem is it's very hard to prove that it satisfies standard product property by using the definition of cohomological action. Basically impossible. And also, it just doesn't work for infinite dimensional modules. It's not fine enough. It always gives you a closed subset, for example. So I need to extend it in a good way. And the way to do it is to use the BAK local cohomology functors, which I'll try to explain. Okay, so Benson and Krause work in much more general setting than what I need here. They have a tensor triangular category T, and then ring R, which centrally acts on T. I'm going to apply this to the situation when R is my cohomology ring, and T is the stable moment. And X project of R. So X is going to be this ambient space where supports live. Now, I'm going to construct universal modules, gamma, associated to homogeneous prime ideals. So for any homogeneous prime ideal in cohomology, for any P and X, we will construct a universal local cohomology module, gamma P K. And we'll do it by actually constructing the functorial correspondence for any representation of G, and sort of cutting it down to make sure its variety is small enough. But first, still hear me? Yes, I didn't turn it? Okay. So in our tensor triangular category, we have the graded home. So basically it's the cohomology ring. So this is a stable home, and we take the direct sum over all shifts of n. And this is just the take cohomology for our finite group scheme. And we have the ring R, cohomology of G, acting on the graded home, once again, by the United product. I need some terminology from commutative algebra. If I write here, people see? Here? No? Yes? Now let Y be an R module. Then we'll say that Y is an P, and is a prime ideal, homogeneous prime ideal in R. We say that Y is P local if the canonical map from Y to its localization at P is an isomorphism. And we say that Y is P quotient if, when we localize Y at any prime ideal which is not contained in P, any prime ideal which is not contained in the Zariski closure of P, so we don't want P in Q, then the localization vanishes. P local objects and P torsion objects. Now, this is in commutative algebra, and I want to transfer these notions to my representation theoretic context. And I'll do it using the cohomology algebra action. Now, in my stable module category, taken on M, so we'll say that M is P local and P is homogeneous prime ideal in cohomology. Right? If, okay, now I can directly localize M with P. I don't have R. I don't have my ring R acting on M, but I have R acting on the graded home or cohomology of M, which is what I'll use. If the graded home C M is P local for any finite dimensional representation of G. So to define P local, I just look at the action of R on the cohomology of M. Then we can look at the subcategory of all P local objects. I think my P's, just like my K's, all the same. All P local objects. This is inside stable model category. And this is a tensor ideal localizing subcategory. Which one can easily check just using the definition. This means that this embedding has a left joint. Which we'll denote by MP. So this is the localization of M and the prime ideal P. The property that it satisfies by construction is that if we try to compute the graded home and localize at P, then this functor uses an isomorphism in the graded home C to M P. So we can go from M to MP. It's a localization of M at P. Now if one tries to compute variety of this localization, forgetting about the fact that I didn't define what the variety is, which is just motivation. If you had a variety, then variety of this localized module will be sitting inside a subset of all those prime ideals which are contained in P. So we sort of cut out everything that doesn't sit inside, which doesn't sit inside P by doing this localization. Okay, now I need one more functor. I want to cut it down further. This is the next definition. Now, we generalized we transferred the local objects. Now we want the torsion objects. So we'll say that M is P torsion if, once again, we mimic the definition that we have in commutative algebra by using the action of cohomology ring on the graded home. So we want graded home localized at any prime ideal which sits, which doesn't sit inside the risky closure of P. So in other words, Q does not contain P. To be zero. So for any Q and any finite dimensional module. So P torsion, if its home, vanishes once we localize anything that does not contain P. Now again, we can look at the subcategory, and I'm going to give it a weird name without really describing why it's that. But maybe it's clear from what we said. So now let's look at the subcategory of all P torsion objects. Again, inside the stable module category, and it has the right adjoint. Then module M to P torsion object. Now the gamma d of P. So M goes to P torsion object. And again, motivation here, that once we do that, our hypothetical support should lie inside the Zariski closure of P. So this way, we get out all ideals, all prime ideals, except for those which contain P. We go into the P torsion object. Gives us this. Okay. Now what I'm trying to do is to construct a universal object such that the support of this object is going to be just P. And basically, This is what I did. We'll define gamma p of m, then for any object in the stable module category, to be, well, first we localize at p, and then we apply our other functor, which makes it a p torsion object. Turns out that we can also do it in the n order. And first take the p torsion object and then localize it. And this is a functorial way to associate to any m object which is going to be p local and p torsion. So this is a functor on my stable module category, and will be known by gamma p, the image of this functor. Everything we get when we apply it, and this is a subcategory of p local and p torsion objects. And they'll play an essential role in the classification of fixed subcategories. In particular, this is a localizing tensor ideal subcategory, and the functor gamma p is a tensor functor. So we can actually write any gamma pm as gamma pk tensor m, just given by tensoring this one object. So this is the object I wanted to construct. Now, to any prime ideal, associate this module, the local cohomology module, and it's a universal construction in various senses. And also might have seen it in a different incarnation. This was actually, for finite groups, first introduced by Rickard, and he called them couple modules. They are also called Rickard idempotent modules. So Rickard, in his seminal paper in, I think, 96, advocated the point of view that topology is hugely underused in representation theory, and we should use more methods coming from topology. And he constructed these kappa modules using Ball's field localization, which is more or less what I was doing here without saying that. So methods are either algebraic or topological. Anyway, this was the thing I wanted. Now I can define maybe here what is the support of a module. Again, I take any module, my stable module category, then the support defined by Antina, Younger, and Crowley, so I'll call it the PAK support of M. So this is an invariant which we are going to construct inside our space X. I think I keep writing the space X and keep erasing. Maybe you can write it somewhere where it will stay. My R is the cohomology ring, and the space X is the prod R. So this is where I'm going to construct my support theories. So this consists of all points in X of homogeneous prime ideals in the cohomology ring, such that if you take M, and tensor is the universal cohomology module associated to the point P, then this is not 0, in the stable module category. In other words, it's not a projective module. So to define the support, I test point by point by looking at the global structure of this module. And then I'm also going to define another invariant, which somehow turns out to be stronger than the support, and which hopefully I'll have time to use to classify localizing subcategories, cosupport of M. And this is the set of all prime ideals in X, such that, okay, now I have to do sort of an adjoint to that. So I take the home. Maybe. We take home from the universal module gamma pk to M and check whether this is trivial in the stable module category or whether it's projective. Now we did talk about the tensor product structure. Again, if you have a Hopf algebra as an antipode, then home, internal home between two modules, home, linear home between two modules, again has a structure of a module for the Hopf algebra. So this is the structure I'm using. Should probably remark that if M is a finite dimensional thing, then the homological support in terms of the action of cohomology in the X group is the same as PAK support and the same as the cosupport. But once you move away from finite dimensional models to infinite dimensional models, all these things are different. They're all different invariants. Okay, let's go back to my table. I'm not going to write down the properties of cosupport, although cosupport actually satisfies all the same properties, except that here I need to have a home property instead of tensor, which I mentioned. But let's start with the support. Here, the PAK support of M. So these properties are always formal. They are little exercises. The realization property is more or less a theorem of John Carlson, which uses this ingenious construction of Carlson zeta modules, which I mentioned on Saturday. But here we have a big problem. So this PAK support arises from the action of cohomology, though it's not explicitly given by the action of cohomology, but this is what it's based on. And just as for finite dimensional modules, we don't have a good way of proving this property using cohomological definition. We can't prove it for infinite dimensional modules either. So, unfortunately, to give the classification of thick subcategories, we need this thing, and it's not there. And the way we're going to solve it is that we will construct another support theory, which basically by design will satisfy the tensor product property. It's going to have some other problems, because life is not perfect, but we'll solve those problems. And then the strategy is then to identify the two theories, which together will have all the properties that we'll need. When am I supposed to stop? Okay. Any questions? enough time to mention the history of the problem. Rank varieties. So this started with John Carlson introducing this rank varieties. This rank varieties for elementary billion P groups. Does it work? Not too loud. So let E be an elementary billion P group of rank N. The group algebra of E is the truncated polynomial algebra. And we already mentioned that the homology of E would be explicitly calculated, and it's also a polynomial algebra on n variables. Tens are the exterior algebra. Just for convenience, let's assume P is not 2. The only reason I don't want to write the different answer for P equals 2, it all works. The variety of space X here is the projective space, and we'll view this part of the homology as the coordinate algebra, homogeneous coordinate algebra. Of P. P and this one. Then this elementary billion P group is a special case of finite group or a finite group scheme. So we have cohomological support varieties here. I'm going to describe them in a very different way. So let's say we have a point, call it lambda, on the projective space. Now we can associate to this point an element in the group algebra, just linear combination of the generators of my algebra with these coefficients. Okay, not to sleep yet, you can argue this is not a well-defined element, but I'm going to ignore that. Now, we can associate it to this. If we add 1, so this element is going to be p nilpotent. If you take the pth power, it's 0. If we add 1, then the pth power is going to be 1. And if we generate a subgroup inside this algebra, this element is just going to be a cyclic group. The pth power is 1. And it's a subgroup in here. So if we take the module M, then we can restrict it to this subgroup. Now these subgroups, called cyclic shifted subgroups, cyclic shifted subgroup of E, and the reason is that it's just a subgroup of the group algebra, not a subgroup of E. Like E only has finitely many cyclic subgroups, whether here we have space of cyclic subgroups, and they're parameterized by the projective space with tons. In fact, the reason that you look at cyclic shifted subgroup, which John Carlson probably wouldn't like, is that this elementary billion P group, it is just a pure-restricted Lie algebra in disguise. So it's really trying to be a pure-restricted Lie algebra, and if you think about it as a pure-restricted Lie algebra, then it all sort of falls in place, and you just can. It's enough to look at P-restricted Lie subalgebras. But if you want to think about it as a finite group, then we have to shift. Okay, then we define rank variety. Do we have an addition for that? No, so I think I formulated this theory. Theorem was conjectured by Carlson and proved by Avrunin and Skov. And I think Avrunin was someone who actually claimed that to call something classical, it has to be at least 20 years old. This one qualifies. So we have the support, homological support, I can say. PAK support let's say cohomologous. M is finite dimensional here. Can be computed as follows. So this lives in X, which is just projective space for elementary B and P group. So we take what is the projective space? Take our module M. We restrict it to the cyclic shifted subgroup defined by this point. And we check whether the result is projective or free. We're in P groups, so projective is the same as free. If it's not free, then we take this point into the variety, and we have one-to-one. So on this side, we have this global cohomological definition. We have a global action of the cohomology algebra or the X algebra. On this side, we have a sort of point-by-point description of the variety, where it all goes down to the representation theory of the cyclic group. And, as we all know, representation theory of cyclic group is very easy. So basically, if you have a question about it, most likely you should be able to answer it. So it's these two different descriptions that actually allow you in the end to get to the tensor product property. And I think what we'll do next time, we'll see how this can be done for any finite group scheme. This kind of local description of the variety. I'll stop here. Thank you.
Any questions over
If you take something in the small, finitely generated scale category, you took the annihilator of a certain molecule to define this formula. So you also get a coherent sheet. But in the infinite dimensional case, you only have the set. You have a coherent sheet.
You certainly won't get a coherent shape. You can get quasi-coherent shapes.
So that's well-defined quasi-coherent sheet.
The annihilator is not quite what you would look at, but you can get quasi-coherent shapes starting with modules in the big stable module category. And basically, it's a little bit of a different story, but basically what you would do is, instead of looking at these things point by point, you can globalize this operator by extending scalars to the coordinate algebra here. And then applying this operator to your module will take you from representations of P to sheaves on the projective space. And then for finite dimensional modules, one can compare at least supports of these two different